Very good. So for this week's particle theory seminar, we're very happy to have Emily Nardoni, all the way from IPMU, and she'll be talking about anomalies of non-invertible symmetries. Yes.
Okay, thank you very much. So today I'm going to say some words about anomalies of non-invertible symmetries. So this topic of generalized global symmetries and in particular quote unquote non-invertible symmetries, which I'll explain what I mean in a moment, has been very active in just very recent years. I know there are some experts in the audience. I'll try to give a talk that's hopefully accessible and explains some of the things that I'm interested in this area. And what I'm going to say is going to be based on some work from this year with my really fantastic collaborators, Justin Kaidi, Gabby Zafrir, and Yunchin Zhang. So please feel free to interrupt with questions. No. Oh.
You can put it on the screen.
Yeah. Hey, there we go. Okay, so in recent years, we've been thinking about sort of a generalized notion of the traditional notion of global symmetries. And so, and the main crux of this line of thought is to think of global symmetries as being implemented by topological operators and to understand how to think about all of the different aspects of the symmetry in the language of these operators. And this is very nice because it lends itself very easily to some generalizations, which I'm going to be interested in. So to explain, let's maybe say the prototypical example of just some continuous global symmetry in some d-dimensional quantum field theory, which has a conserved current. Then the global symmetry can be thought of as implemented by operators, which are constructed as follows. First, I integrate the conserved current over a d-1 dimensional submanifold of space-time, and this gives me my conserved current, or sorry, my conserved charge. I'll ignore Noether's theorem, and then I exponentiate this conserved charge, and this gives me an operator, which is the analog of the unitary operators from quantum mechanics that act on my Hilbert space and implement the symmetry. And these operators depend on the submanifold over which I've integrated, as well as on the group element of the global, and they're also labeled by the group element of the global symmetry. Here I've explicitly written some example for, like, for example, a U1 global symmetry, but you can of course do this more generally. And so the important comment is that these operators depend on this submanifold only topologically. So they don't change with like small wiggles, and unless as long as I'm not crossing like operator insertions that are charged under the symmetry, they only depend topologically on this manifold. And then we can understand in this language how to act on local operators that are charged under the global symmetry, and that's by linking with the charged operator. So I can think about linking my my symmetry operator. Maybe I'll refer to this as a symmetry operator or a topological defect operator with the charged operator, and in doing so, my operator transforms up to the appropriate representation of the symmetry group. This is labeled by the group element. Okay, so like I said, the main motivation for rephrasing what we know about global symmetries in this operator defect language is because it lends itself very nicely to generalizations. So firstly, I've written some explicit formulas here for continuous global symmetries, but These symmetry operators can also be defined for finite symmetries, even when I don't have this conserved current to fall back on. And also, they can be defined for higher form symmetries. So the formulas I wrote on this slide were for so-called zero form symmetries, but I can also have symmetries that act on extended operators in space-time. So a Q-form symmetry would be defined by its symmetry operators, which live on codimension Q+1 submanifolds of space-time and act on Q-dimensional extended operators in my space-time. And so in this talk, I'm going to be considering both examples of both of these, finite symmetries and higher form symmetries. Yeah. Now for our usual symmetries, these symmetry operators satisfy fusion rules in accordance with the group multiplication law. So basically, if I think, so also, by the way, I'm going to draw some pictures as if my defect operators are lines, which is true, for example, for a zero form symmetry in 2 dimensions, but this is just some picture. You can imagine drawing more complicated pictures for higher dimensional objects. And so I can fuse together two symmetry operators. This is basically, I put them parallel to each other and I bring them very close, and then I can think of the composite operator of bringing these two guys close together. This is basically the OPE for extended objects, extended operators. And when I do so, the operator I get out is labeled by the composite of the two group elements that I brought in, according to the group multiplication law. And similarly, if I fuse an operator with its inverse, I get the non-line or the identity. So I can phrase this group multiplication law in terms of this fusion language. Yeah.
So the arrow that you're putting the line is like the orientation of the manifold.
Yeah, that's like the orientation.
So it has opposite orientation is the inverse element.
Yeah, at least in a basic example. Yeah, that's right. And so this sort of discussion leads to a very natural generalization, which is to relax the requirement for invertibility in this group structure and consider defects that are governed by, instead of a group, a fusion category or a higher fusion category, depending on what dimension I'm in and what sorts of operators I'm considering. And so basically, I still have other things I like associativity, but I've lost the requirement of invertibility of the defect operators. So, for example, I would have some fusion structure where when I fuse two of the defect operators, I can get a sum of other symmetry operators in the theory governed by these fusion coefficients, which tell me about fusion of 3 of these, in this case, lines together. And so when I have this sort of structure, not every line in the theory will have an inverse. And so I'm going to refer to a global symmetry with such a more generalized structure as a non-invertible symmetry or a categorical symmetry. People use different words to say these things. And in recent years, people have been studying these especially in 2 dimensions, and then also more recently in higher dimensions. Of course, some people here are actively working on this line of work. So the big interesting questions, once I know I have these sorts of operators in my theory, are how do the many utilities of group-like symmetries extend to these non-invertible symmetries, first of all. So of course, global symmetries are great. They can provide many constraints on physics and we've learned lots of tools. for how to constrain physics and theories based on group-like symmetries. So how does everything we know about group-like symmetries carry over to the non-invertible case, first of all? And then second of all, by knowing about these non-invertible symmetries and field theories, can we get new constraints on dynamics that we couldn't have gotten from just thinking about the group-like symmetries? So these are big questions that lots of people are trying to answer. And my goal today is really very modest. So today I'd like to discuss a set of simple observables that constitute a sufficient condition for the existence of a Hooft anomaly of a non-invertible symmetry in general D dimensions. So of course, Hooft anomalies, which I'll say more about in a moment, are a really important piece of data for constraining dynamics of quantum field theories. And so you should ask, what can we learn about Hooft anomalies of non-invertible symmetries? And so today I'm going to tell you about one basic test you can throw at a quantum field theory with a possibly non-invertible symmetry in D dimensions to test for the presence of such a Hooft anomaly. That's the goal. And I'm going to do this utilizing a topological quantum field theory in one higher dimension from my QFT of interest. That's been dubbed in recent years the symmetry topological field theory, and I'll explain what this is and why it's useful in the talk. And so for the rest of the talk, I'll first remind you about anomalies for invertible symmetries and why they're so great and how we describe them using anomaly inflow. And then I'm going to introduce this notion of the symmetry topological field theory and how we can use it to say something about anomalies for non-invertible symmetries. And then I'd like to give some set of examples in four-dimensional gauge theories where we can throw this test at it and see anomalous non-invertible symmetries. So I'm especially interested in this higher dimensional case where much less is understood so far about these non-invertible symmetries. So are there any questions before I continue? Yeah.
Could you say a bit about what class of, like, I know there's like a zoo of constructions for non-invertible symmetries. Which ones can you study with this technique?
So I can study anything for which I can explicitly construct a symmetry topological field theory. So that's the basic statement. If I can, in many cases, I can construct such, or I know how to construct this object, and when I know how to construct this object, then this could be, then this is a useful test you can apply. But and then I'll give some more specific examples.
So in 1+1D, you can always take the center for a fusion category. Does that also apply in higher dimension?
Yeah, so in general, the symmetry TFT is the Junfeld center of the fusion category. That's always true. If I have an explicit construction for the action of this TQFT, furthermore, then I'll be able to use this sort of criteria that I'll explain. Okay, so first let's discuss Hooft anomalies for invertible symmetries, and specifically I want to focus on the perspective of anomaly inflow. So a quantum field theory has a Hooft anomaly when a global symmetry is preserved classically, but not quantum mechanically. Of course, in this talk, I'm focusing pretty much exclusively on global symmetries. An anomaly in a gauge theory would render the theory inconsistent. So that's not what I'm talking about here. Really, you should think of the anomaly as an obstruction to gauging the global symmetry. And so the useful perspective, or an often extremely useful perspective, is to couple the background gauge field for my global symmetry, so some classical background gauge field to my theory. For example, in the most basic case, this would be some my usual like coupling to the current in the Lagrangian. And then there's going to be an anomaly in the global symmetry if I cannot do this coupling in an invariant way relative with respect to the global symmetry. So in particular, if I under a background gauge transformation, if my partition functions transforms up to a phase where this phase alpha depends in general on the background gauge field of the of the global symmetry, and if I can't cancel off this phase with local counter terms, then I have an anomaly. And in particular, this implies that gauging the global symmetry is ambiguous. So if I want to try to promote this background gauge field to a dynamical gauge field and sum over it in the partition function, like do the path integral over this gauge field, then if these configurations are related by these background gauge transformations, this is just ambiguous. So it's in that sense that the anomaly is an obstruction to gauging the global symmetry. And of course, Hooft anomalies are really useful because they provide very powerful constraints on renormalization group flows. They're invariant under continuous deformations of my theory that preserve the global symmetry. And so in particular would be invariant under renormalization group flows that preserve the global symmetry. And so this leads to really constraining statements about, for example, IR phases of gauge theories. And in particular, one such statement you can make is that any theory with a non-trivial anomaly cannot flow to a trivially gapped vacuum with no like long-range degrees of freedom, like a unique trivially gapped vacuum. That's like one example of like the most basic statement you could make, because such a vacuum could not match the anomaly upstairs. Of course, you can make more refined statements knowing the full set of anomalies that my theory has. Did you have a question?
Yeah, so these non-invertible symmetries, are they usually continuous? Are they discrete? They can be both.
They could be both, and in this talk, I'm going to only give examples of finite, discrete, non-invertible symmetries. Yeah.
So what's the best way to think of sort of discrete symmetries here?
So actually, here. So for finites, okay, so I gave some description that seems most applicable to continuous symmetries on the previous slide, but I really want to emphasize that like this applies equally well to finite symmetries. In general, I can think about coupling my background gauge field, which is a flat background field or a background field for a flat connection in the finite case, as inserting a network of my symmetry defects. And so in general, like I said, my global symmetry is like this collection of defects, and coupling to the background gauge field is inserting a network of these defects. And then gauge transformations are like changes of basis of this network. They're local deformations of this network of defects. And so then in this language, gauging the global symmetry, which is could be finite, is equivalent to summing over all possible gauge and equivalent defect configurations. And so in this language, it makes perfect sense to think about like all symmetries on equal footing, including finite symmetries, including non-invertible symmetries. In 2 dimensions, the picture is that I can fix some triangulation of my space-time manifold, and then these gauge transformations are captured by F symbols that describe the associativity of networks of the symmetry defect that I'm going to sum over, and then the anomalies are captured in a specific way that I won't spell out right now, basically by these F symbols. But this is the general picture to keep in the back of your mind, and this works perfectly well for all the sorts of generalized symmetries I might care to think about. Now, from some perspective, I'd say from the modern perspective, but perhaps a very useful perspective on anomalies of QFTs is to describe the anomaly by a TQFT in one dimension higher than space-time, where my d-dimensional space-time lives on the boundaries of this d+1 dimensional space, and that's in the language of anomaly inflow, where the anomalous phase in my boundary quantum field theory, the phase I wrote on the previous slide, is exactly canceled by the action of this anomaly, this TQFT that I'm just going to refer to as the anomaly field theory for lack of a better term, which is invertible via anomaly inflow. So if the action, so the action of this invertible TQFT, which is in d+1 dimensions, so I'll call it omega, depends on the background gauge field for my global symmetry, and is constructed exactly so that under the background gauge transformation, it transforms up to exactly the piece that will cancel off the anomalous transformation in the my QFT's partition function, so that collectively the partition function of this guy and of my d-dimensional QFT is invariant under the background gauge transformation. And so this is, I mean, depending on your bias, this might be familiar from different things. One thing that that might be familiar is the story of the anomaly polynomial for local anomalies associated to the chiral action of my global symmetry in even space-time dimensions. So chiral fermion anomalies are well known to be encoded in a d+2 form characteristic class known as the anomaly polynomial. In this case, the anomaly polynomial is exactly the basically d of this action, and so the anomaly polynomial is the boundary term of basically the Chern-Simons action for the global symmetry in one higher dimension. So, for example, for a U1 anomaly in 4 dimensions, this action will look like 5D, like basically the 5D Chern-Simons action, like A, DA, DA, and this chiral anomaly would be captured by these sorts of triangle diagrams. So maybe this story is familiar to you, and this inflow story is familiar to you. But really, I want to emphasize that this picture of anomaly inflow to describe anomalies of quantum field theories it's more general than this. It holds in any dimension for purely bosonic theories, and in general, thinking about these we call them SPT phases. Is the way to classify anomalies in general dimensions. So that's the so that's the picture. Now, okay, so that's kind of all pretty standard. Now we're interested in non-invertible symmetries, and these can also, of course, have Hooft anomalies. And by Hooft anomaly, I mean what I said on the previous slide. I mean an obstruction to gauging. So gauging in the sense of, so I sum over defect configurations, or I insert a network of my defects which generate the non-invertible symmetry, which satisfy these non-invertible fusion rules, and an obstruction to doing so, I would call it a Hooft anomaly. However, in this case, there are some immediate questions. Firstly, it is not clear how to define a background gauge field for the non-invertible symmetry, or at least I don't understand how to do so. If you do, I'd love to talk about it. Nor is it very clear how to necessarily couple to an anomaly field theory with an explicit local action that I can write down. So this sort of picture that I drew, there is some anomaly inflow picture, but the details of this picture are much less understood and clear for the non-invertible symmetries case. However, in 2 dimensions at least, anomalies for non-invertible symmetries have been relatively well understood and characterized. So these authors formulated some mathematical equivalents to the statement of there being an anomaly in 2 dimensions, and there is an anomaly if there's a lack of a so-called fiber functor. I don't want to get into these details, but there is such a theorem discussed by these authors. And then more recently, Clay and others in the room have characterized the existence of an anomaly in 2 dimensions with, again, like a full if and only if statement, using also this object that I'll introduce on the next slides, the Symmetry TFT from studying basically Lagrangian subalgebras of the Symmetry TFT. So that's really interesting. And I'm interested to understand how these stories can be generalized to higher dimensions. The general statement as it stands, though, is that anomalies for non-invertible symmetries are much less understood in dimensions greater than 2. And so we might be especially interested in exploring if there's something definitive we can say in higher dimensions. And so that's what I want to talk about. And like I said at the beginning, the tool I'm going to use is this D+1 dimensional topological quantum field theory known as the Symmetry TFT. And so now I'll describe what this object is and why it's useful and how we'll use it. So are there any more questions before I continue? Yeah.
Could you explain like the logical implications between your technique, the Lagrangian subalgebra result and the fiber functor? Like which one implies what?
Theirs would imply ours. Yes. So ours is a sufficient condition, and it should be implied, or it should be a corollary of the if and only if conditions.
The fiber functor one is if and only.
Yes.
The fiber functor one, though, is more like a definition. It's more like just saying like the theory has an anomaly, like a fiber functor means realizing the symmetry in an SQT. So like
That's
it's
true.
not, there's like not, I don't know if there's like that much content to that one. And
Yeah, I think, yeah, one could debate, indeed. So yeah, they basically like give an equivalent, like they state, like you say, that a fiber functor, like where the lack of a fiber functor equals an anomaly, and they have reasons for saying so, and then can classify whether or not there is such a fiber functor. I mean, Clay's work is much more related to the sort of is much more in the vein of the sorts of things that I'm going to talk about that are much more physical and really this, I mean, like this work, like your work is like an if and only if statement about as I understand it, about anomalies in 2 dimensions. Yeah, but more questions. Okay, so the Symmetry TFT basically is an object that I can get by blowing up this this picture I have of my QFT on the boundary and my anomaly field theory, or like SVT, connected to it in one higher dimension over an interval. So I have this sort of slab picture where over on the left-hand side hangs out this possible anomaly field theory whose action I reproduced here. And then I have this D+1 dimensional TQFT that lives here, and I apply boundary conditions on either side of this interval or this slab. On one side, I apply topological boundary conditions or daft boundary conditions, and on the other side, I apply dynamical boundary conditions or basically enriched Neumann type boundary conditions that capture the local dynamics of the quantum field theory. And this picture is exactly constructed so that when I shrink the slab, which I could do because it's a TQFT, it's not supposed to depend on the size of the slab, I get out effectively my my original QFT picture that I started with. So what is the symmetry TFT? Well, I already said in general, it's the Drinfeld center of the generally categorical symmetry. In more concrete terms, it's basically a gauged version of the anomaly field theory, basically. So whenever I have this picture with this, for example, with this explicit anomaly field theory, basically just gauge all of the fields that were background fields in this picture. So I've promoted this background A to a little a, it's coupled to its quantum.
But typically that would not result in a topological field theory, right? Like if you just started with like the standard triangle anomaly and did that, it wouldn't be a topological field theory. Or at least we wouldn't, not a standard, like we wouldn't know what we're doing. 5D Chern-Simons theory for a U1 gauge field, I'm not sure we know what that really is.
That's true. So this sort of explicit picture, I have in mind these sorts of examples, especially with like finite global anomalies, where I really like can write where I really mean that it is a gauged version of the anomaly field theory. The definition of the symmetry TFT is not literally gauged version of the anomaly field theory.
Is there a definition that encompasses all cases?
I mean, it's the Drinfeld center. It's like the I would consider that like the basic definition. It's the TQFT.
But does that make sense when the symmetries are continuous? Like, is there such a notion? I'm not sure there's such a notion. Precisely speaking, I don't know. It's like the generalization of this concept to like the continuous symmetries, which is perhaps a vacuous statement. That's like one of the, I think, kind of question, that's one open question, is how to make this sort of explicit in some other types of examples. And the types of examples I'll consider here, I'm only going to actually talk about anomalies for finite symmetries, and this is going to be extremely explicit. And
I just want to understand what you mean by this. So A hat is just enforcing the flatness condition, and little a and little.
Oh yeah, indeed. So this is like the dual like quantum symmetry from gauging this this symmetry. Again, I have like finite symmetries in mind, and indeed it enforces the correct flatness condition on this A. And I'm being completely glib about normalizations and stuff, but in example, like in any example you want to consider, you should have the right normalizations, and these might be the cocycles.
When you impose this topological boundary condition, how do you pick it?
Good, so I'll say that in a moment. Just ask me again in one slide. Okay. And so, but first, one comment I want to make is one of the reasons this is so useful for us is because the symmetry TFT is invariant under all topological manipulations of my quantum field theory. So for example, gauging, like for example, stacking with other TQFTs. And because of this, it's easily computable in cases where even for my non-invertible symmetry or higher categorical symmetry, if it becomes invertible in some frame, and I have such a background field description, and I can do this sort of explicit like construction of the symmetry TFT, then I know what it is explicitly, even for the non-invertible case, if they're continuously connected by such topological manipulations.
It's an open question in general, how to do this in other cases. I mean, like this work studied how to describe the symmetry TFT for general non-invertible symmetries with some caveats. But in general, I don't have such an explicit construction, and so this is less useful. But these are sorts of like active things that people are thinking about. But that's particularly why this is going to be so useful for us. And so I said that I'm imposing boundary conditions on either side of this slab. And so let me especially highlight these topological boundary conditions. So the main statement and the other reason that this is so useful is because the symmetry TFT and together with these topological boundary conditions, these capture the generalized symmetries of my quantum field theory of interest. And so so that's why this is so interesting. Now, for the topological boundary conditions, I could impose like Dirichlet boundary conditions or Neumann boundary conditions or some mixture of Dirichlet or Neumann boundary conditions. And so one thing I could do is I could fix by imposing Dirichlet boundary conditions for my background field, I would fix the fluctuating or the dynamical gauge field in the bulk symmetry TFT to its background field value on the boundary. For Neumann boundary conditions, I would allow this gauge field to fluctuate on the boundary, but that's what I mean by imposing gap boundary conditions. So those are the sorts of choices I have. Okay, so I have the symmetry TFT.
Why is it important to impose the second boundary?
The second boundary?
Well, usually when I think about anomaly inflow, I don't imagine that there's a second boundary. I just think that
Of
there's
course.
physical theory, there's something going out over there, I don't care. Why don't we just have the same picture? For, like, there's the physical theory, there's some TQFT here. Why do we care about this other boundary?
So, okay, so from my perspective, let's say wanting to know about anomalies of like non-invertible symmetries. Like if I understood, if I knew how to characterize these anomaly field theories in general, I wouldn't need such another boundary, right? Like I wouldn't need the symmetry TFT to say anything about the anomalies. But instead, like I don't know like how to write this anomaly field
Right, most of
theory.
the time, I think the picture on the left just doesn't exist.
Exactly.
And then you just have the picture on the right, but maybe without the other, why do you need the other boundary in that case?
Well, in terms of
Like,
I-
why don't we just upgrade our understanding of what anomaly inflow is to say that anomaly inflow is a non-topological field theory on the edge of the topological field theory.
maybe that's what we should do. I mean, like, or so the reason we quote unquote need the topologic or the other boundary is simply that this construction, when smushed, gives back the original quantum field theory. Maybe I don't have to think about it hard. I don't have to think about it at all for like anything I'm going to say in this talk, but it's there because if it weren't there, then I couldn't actually smush this to get back my quantum field theory. So in some sense, one might argue that this is the upgraded notion of anomaly inflow for non-invertible symmetries. And I'm kind of sympathetic to that point of view.
Like, I think there probably isn't a notion of background fields in general for them. There probably isn't a notion of an invertible bulk in general.
That might be true. But I don't know, maybe we could talk later.
Okay.
For me, this is the most interesting question about this. Like, I am interested in understanding like what is the statement of anomaly inflow for non-invertible symmetries? And maybe the answer is that it's the symmetry TFT picture and that's as good as it gets. But I don't know, maybe not.
Okay.
But yeah, I mean, it's also a good statement because that's part of the reason that the symmetry TFT is so useful. Like maybe one way to think about it is like the version of anomaly inflow for non-invertible symmetries. That's certainly a valid perspective. So I have the symmetry TFT and it itself has its own set of topological operators, right? So it's this D+1 dimensional system. And the statement is that the topological operators in this bulk symmetry TFT can be divided based on whether or not they end on the topological boundary. So what we're going to do is divide the operators into two sets. So here I'm drawing some picture, like the bulk is like the symmetry TFT, and this is like the topological boundary. So that's why I said, like, what I'm saying, like, this other boundary doesn't matter. It only matters in the formal sense. And so one possibility is that my bulk symmetry TFT operator, it's some possibly extended operator. It depends on some like P dimensional submanifold of the G+1 dimensional bulk can end or terminate on the topological boundary, on some like P-1 locus of the topological boundary. So this would be the case, for example, if this bulk operator, like say this bulk operator is some like Wilson line for like the gauge field A in the bulk. If this A had Dirichlet boundary conditions, so it's just set to some constant value on the boundary, then that would be the case that this sort of operator was able to terminate on the boundary. So it belongs to the Lagrangian subalgebra associated to that topological boundary condition. Alternatively, it could be non-terminable. If it doesn't terminate on the boundary, then it is attached to some operator that lives on the boundary, to some boundary operator. This boundary operator, I'm here denoting the boundary operator in green. This would be the case, for example, if this gauge field, if this were my operator in the gauge field satisfied Neumann boundary conditions, so it could fluctuate on the boundary, then I'd actually have some boundary operator connected to the bulk symmetry TFT operator. And the statement is that these non-terminable bulk operators, when I shrink the slab, exactly give me these boundary operators, which upon shrinking are exactly the symmetry operators in my original quantum field theory that generate the boundary, like general categorical, like whatever generalized symmetries of my quantum field theory. So from the symmetry TFT point of view, that's where those symmetry operators in the quantum field theory come from. So let's do a quick example. So for example, let's say we're thinking about 4D SUN Yang-Mills theory. There's no anomaly, so I didn't draw an anomaly. And so this has some one form ZN symmetry associated to the center of the SUN gauge group. And so that's generated by some topological surface operator in my theory, which is constructed from this from the background gauge field for the ZN one form symmetry. Okay, so in the symmetry TFT, so now I expand out the slab picture. What is the symmetry TFT? Well, I just gauge this. So upon gauging, I get some basically topological like two form gauge theory, and so with this sort of so in general, with these sorts of examples that I'm thinking about, I'm going to get these like Digraph-Witten type actions, and then by imposing Dirichlet boundary conditions on the topological boundary, I set this dynamical gauge field in the bulk equal to its background value. That's what I would do in order to shrink the slab and get back the 4D SUN Yang-Mills theory that I started with. So now I can look at the surface or at the operators in general and the symmetry TFT, and I have bulk surface defects. In particular, I have the surface defect, maybe I call it the electric type surface defect, by integrating the two form B gauge field in the symmetry TFT, and I have the like sort of magnetic type surface defect. And the statement is this electric type surface defect, because of the Dirichlet boundary conditions, can terminate on the boundary. It belongs to this red class. This other defect does not. It belongs to this blue class. Instead, it ends on, you can check exactly the operator that will generate my ZN one form symmetry in my original quantum field theory when I shrink the slab. So that's a simple example. However, there's no anomaly in that example. So let's try a case with an anomaly. To do so, let's gauge a normal subgroup of my ZN one form center symmetry. Upon doing so, my global symmetry is now the remainder, like Zn mod Zn over 2. That's one of these guys. And I have the dual like quantum
Z n over 2 one form symmetry. So now I have, by gauging this normal subgroup, I have this, this global symmetry, and these two factors have a mixed anomaly. The mixed anomaly looks like this. It's some coupling of like the two background gauge fields. So here I've just kind of written the inflow action for that describes this anomaly. So gauging this normal subgroup changes the boundary conditions. That changes the topological boundary conditions from Dirichlet boundary conditions to now like mixed Dirichlet-Neumann boundary conditions for these now two background gauge fields. But it didn't change, and it changed the anomaly field theory. Obviously, now I have a theory with an anomaly, so I have this like SPT hanging out. But it didn't change the symmetry TFT. So the symmetry TFT is what I wrote on the previous slide, and all of these background gauge fields can be related to the ones on the previous slide by appropriate in the appropriate way. And so I can look at my bulk surface defects. I have the same bulk surface defects as the same symmetry TFT. Now you can check that the Wilson surface type operator, which was in the red class, is now in the blue class. Now it exactly maps onto the operator that generates the one of these Z n over 2 symmetries. And meanwhile, the magnetic type operator, which when I smush the slab, exactly becomes the generator of the quantum Zn over 2 one form symmetry. So you can just, this is sort of a simple example. If you want to sit down and check for yourself, you can check that all of this works out nicely in this example. Okay.
So your symmetry TFT doesn't change, the boundary conditions change, and that's sufficient to reproduce the anomaly.
So like what you can check is that so it's not that the boundary conditions change and that's sufficient to like produce the anomaly, but like I can check that now, like with all the changes of variables and doing the sums and with the change of boundary conditions, I guess yes, yeah. I guess the answer is yes. Like you can check that I exactly reproduce this form for the anomaly. So yes, in some sense.
How would you you have a different anomaly field theory in this case?
Yeah, before the anomaly was trivial, so there was no such leftover 5D action after the topological boundary condition. And the statement is now I get this leftover action. But yeah, like I like this example just because it's like something you can really just sit down and like check for yourself. And it's in 4D, which is nice. Okay, so now let me state like the main observation. So okay, we have a quantum field theory. It has some non-invertible symmetry. This non-invertible symmetry is say generated by or not non-invertible symmetry. It has some general categorical symmetry, and it's generated by topological operators in my quantum field theory. Therefore, the associated symmetry TFT contains operators in the bulk that end on these symmetry operators. Now, suppose that my symmetry is anomaly free and then can be gauged. So therefore, in this case, the corresponding bulk operator should become terminable on the topological boundary. Otherwise, I can't gauge it if I'm left over with something dynamical. Now, this is only consistent that the bulk operators become terminable upon gauging the symmetry if the braiding of the operators in the bulk is trivial. And that's exactly because, like, say I have operators in this red class that are terminable on the topological boundary. Everything's topological. I can move them around each other. I shouldn't get any sort of phases, like these sorts of correlation function. Oops, not mean to do that. These sorts of correlation functions between the bulk terminable operators should be like 1. So therefore, the anomaly is probed
by these sorts of bulk correlation functions. And maybe this is an obvious statement, but the main observation is that therefore, if you cannot find a representative bulk operator in my symmetry TFT that has such trivial link invariants or such trivial correlation functions, then the associated non-invertible symmetry is anomalous. So this is sort of a testable version of this idea which is not new, which is that the anomaly is probed by bulk correlation functions of the operators. That yeah. So is that logic clear? I hope. So some immediate comments are, first of all, this is a sufficient condition for a non-trivial anomaly. So however, it is not necessary. So there are examples where I can't probe the anomaly of the symmetry from such a condition. Maybe like because the codimensions of the objects don't work out. That's certainly possible. And it is strictly weaker than the conditions of these other works, including the one by Clay et al. And so those are, again, definitions or if and only if statements, and this is a sufficient statement. So, so this is weaker. The upshot is that this is a test I can apply in general D dimensions. And like I said, it can be especially useful in these scenarios where I know the symmetry TFT as some digraph Witten theory, possibly with twist. And in such a scenario, these link invariants are very easy to compute. And so this is imminently computable in some situations of interest.
How do you know which lines you want to end at the boundary? Because like, for example, if you take Tambara Yamagami, there's like G duality lines in the bulk.
Yeah, so in any given example, you'd kind of have to test, like you have to check which are the lines that will end to give you the symmetry. I mean, you would need to check that the line you get when it ends on the boundary, like, is the thing that generates the symmetry in the quantum field theory. You'd have to like check that, and then you'd have to check that there's like no representative of these lines, like there's like some equivalence class like statement here that gave you the like the trivial correlation functions. So there are some things to check. So yeah, in your given example, you'd have to check these things. Thank you. So for example, like let's take this example that I was just giving you of 4D Yang-Mills theory with the where I've gauged the normal subgroup. So there, remember I said that I have these sorts of surface operators in the bulk symmetry TFT that on the boundary generate my boundary one-form symmetries. And I said there was a mixed anomaly for these. And so the statement is that in this example, this mixed anomaly is probed by a two-link invariant of exactly these surface operators in the 5D symmetry TFT. So you can check this, you can do this correlation function and check that I get something non-trivial. It's some phase that goes to the linking number between these two surfaces. So that's an example. But I can go beyond links just involving two lines. The general set of things I can probe are, say, two component sorts of links, which are possible. I mean, you could do some codimension counting problem that like I can, that closed surfaces of various dimension can link in, say, q dimensions if this condition is satisfied. So for example, for lines in 3 dimensions, I could probe the anomalies with these sorts of linking configurations. I could also have like higher component links, like for example, 3-component links. So, and there's some statement about the relative dimensions or codimensions of these objects where I could probe such a configuration if all of the dimensions satisfy this relation. So for example, for lines in 3 dimensions, the Borromean ring type of configuration could be probed by this sort of correlation function. So that's just a comment on the sorts of things you can probe. So I'm almost out of time. Let me just end with an example.
You got about, 8 more minutes.
Okay, okay,
Starting companies.
okay, cool.
Plus 5 grace minutes. Yeah, just go for it. Don't worry about it.
Okay, cool. So let me give my favorite example. Let's consider, so before I gave some examples of like invertible cases, so only invertible symmetries. So let's construct a non-invertible example. So say we have a 4D quantum field theory with a global symmetry group that includes some sort of one form symmetry and a zero form ZM, like finite ZM symmetry with background gauge field A. So say I have such global symmetries and say that I have a self anomaly for the ZM symmetry, the zero form symmetry, and a mixed anomaly between the two of them. Yeah.
Self anomaly.
Good. So I mean exactly something like this, like a qubit. So in 4 dimensions, this would be some like, I mean, ADA, or like the finite analog of the ADA type coupling. And so right off the top of my head, I can think of 2 examples. One example is adjoint QCD or adjoint QCD. And another example is n equals to 4 super Yang-Mills. I'm not going to talk about the n equals to 4 super Yang-Mills example, but let me mention the adjoint QCD example. So for example, by adjoint QCD, I mean 4D SU gauge theory with some number of adjoint Val fermions. I have a ZNC for the number of colors, one form center symmetry, and I have a Z to an FNC zero form symmetry, which is the remnant of the U1 axial symmetry after the ABJ anomaly. And in such a case, I have an anomaly inflow action, which describes the mixed anomaly between between these 2 guys. Here A is the background field for this guy, B is the background field for the one form symmetry, and the pentragon, and this is like the appropriate quadratic form for B. And then I have a self anomaly, by which I meant like some term like ADADA in this example for just the Z to an FNC symmetry with appropriate factors, and this expression changes slightly between even and odd n, but okay, but there's such an expression for these anomalies. So first, so that everything's invertible so far. So first, let's gauge the one form symmetry, and in doing so, I can promote in examples such as this example, my zero form ZM symmetry to a non-invertible symmetry. And this non-invertible symmetry will be implemented by a non-invertible defect, I'll call it like Hurley n. So first I'm going to do some gauging to give me a theory with a non-invertible symmetry. And this is one example of a case where this works out. And so in the Symmetry TFT picture, I'm doing some gauging, and and I mean, like I don't know how to think about this quote unquote anomaly field theory in this case, but in any case, I can think about the gauging in the Symmetry TFT picture. Then step 2, I can ask whether or not the non-invertible symmetry is anomalous. And naively, you expect it should be anomalous because it kind of originates from the invertible symmetry, which had a self anomaly. So like your gut should tell you it should be anomalous. And it is, and the fact that it is can be probed by link invariants in the Symmetry TFT of the type that we've been describing. So for example, in this 4D adjoint QCD example, you can go through the exercise. So you can write down all the different defect operators in the 5D Symmetry TFT before gauging first. So I have basically 2 types of operators. I have electric type operators that can terminate on the topological boundary, that I have like line operators made out of the A background gauge field and surface operators made out of the B background gauge field, or in the bulk dynamical gauge fields. And then I have magnetic type operators, which are both surface and volume type operators that are actually non-invertible operators in the bulk symmetry TFT. So far nothing's non-invertible in the boundary QFT, but there are non-invertible operators already at this level in the symmetry TFT. And so they're non-invertible because they're made out. So they're made out of these like dual gauge fields, and then they have these like TQFT bits tacked on, which mean that they satisfy non-invertible fusion rules with the other defects. And it's precisely these non-invertible defects in the bulk symmetry TFT that reduce to the boundary defects generating the 1 form and the 0 form symmetries of my QFT. And so then we do step 1, we gauge our center symmetry, and this promotes the SUN gauge group to PSUN gauge group. So this is now PSUN adjoint QCD with a now like quantum Z, call it Z hat, 1 form center symmetry, and now a non-invertible defect, Curly N, studied by these, this sort of construction was studied by these groups. And when I do the gauging, again, my symmetry TFT stays the same, but I can check what happens to the operators. So one of my magnetic operators moves into the Lagrangian subclass, and one of my electric operators moves into the blue subclass. And so now I can check that the operators that reproduce the symmetry operators of this gauged theory are one of them is the electric this electric surface operator, and one of them is which is generating the Zn hat 1 form symmetry now of my quantum field theory, and the other is this in the bulk non-invertible volume operator, which on the boundary reproduces the non-invertible volume operator, which generates the now non-invertible defect in my quantum field theory. And so then I can compute a correlation function between these guys that reproduce the non-invertible defect in the quantum field theory, and I get exactly this sort of non-trivial phase, which depends on the linking of the three surfaces or 3 volumes on which the operators depend. And so based on the form of this coefficient, which depends on NC and NNF, I would conclude that 40 PSUN adjoint QCD has an anomalous non-invertible symmetry for all NC greater than 1 and NF greater than or equal to 1. And so that's a sort of statement you can make. Of course, I would have known that this theory had an anomaly, at least for most values of NC and NF, but because of the form of this coefficient, this does rule out some like super special values. So you can debate how much information you've gained here, but anyways, this is the sort of statement you can make. And so I just wanted to end with a comment on matching these anomalies in the IR. So for example, let's take this like adjoint QCD type of example. Let's take the NF equals to 1 case, which is of course has an enhanced supersymmetry and is n equals to 1 super Yang-Mills in 4 dimensions. So in this case, this Z now NF equals 1, so Z2n 0 form symmetry is the R symmetry of my n equals to 1 super Yang-Mills, which is spontaneously broken by the Gaugino condensate in this well-known story to a Z2 subgroup, and this breaking pattern leads to NC gapped supersymmetric vacua of n equals to 1 super Yang-Mills. And so these are my n vacua, and there are domain walls that separate the vacua, and these domain walls support some 3D Chern-Simons theory that depends on the background gauge field for the 1 form symmetry. And the statement is that these domain walls match the mixed anomaly between the 1 form center symmetry and the Z2NC R symmetry. So the anomaly of this form that's matched on these domain walls. And so then you can ask, how is the self anomaly matched? So I said there's also this self anomaly of this theory, the cubic zero form symmetry anomaly. So how is that matched in this picture? And so the very simple comment that I'll make is that one way to think about this is in the language of the symmetry TFT. And so I'll make some schematic comment here. And that's that, so I can understand this RG flow between n equals to 1 SUNC superunion mills and the NC gapped vacua in terms of this symmetry TFT picture. And okay, in the UV, I have these like gapped boundary conditions on this side of the slab. And the statement is that in the IR, because I flow to gapped vacua, the enriched Neumann boundary conditions on this side have to become gapped. And because of the symmetry breaking pattern of the Z2NC zero form symmetry, its operator, the operator associated to that symmetry should terminate on both sides of the now both topological boundary conditions. And because the one form center symmetry is unbroken in this phase, we expect it to satisfy Neumann boundary conditions on this side of the interval. And so basically what's happening in terms of these operators in the bulk is that this red line operator is becoming in the IR the order parameter for the Z2NC zero form symmetry, that the one that labels the NC vacua, and this non-invertible volume operator, the one that becomes the Z2NC defect, exactly becomes the domain wall between the vacua. So you can check that the TQFT part of this guy exactly is the domain, is this Trans-Hyman's term on the domain wall. And then the fact that I have a self anomaly is related to the fact that these domain walls that host this non-invertible symmetry or this defect associated with non-invertible symmetry, these domain walls and their junctions should exactly when restricted to the boundary saturate this self anomaly. And so this can be probed, for example, by looking at the triple link invariance between these operators. So kind of like the straightforward observation is just that like one way to think about how to match a self anomaly is in terms of the link invariance or braiding of these operators in this bulk symmetry TFT. And so this would be the sort of like this would be interesting to work out in detail. Okay, and I think even with my generous few minutes I went over, so maybe I'll just summarize. Much like for ordinary symmetries, like I said, Hooft anomalies of non-invertible symmetries are a useful tool for constraining the dynamics of quantum field theories. And I explained that linking invariants in the symmetry TFT can provide a diagnostic for these anomalies for generalized symmetries. And in some examples, they're simple to compute. So I gave the example of adjoint QCD here. Another 4D example is n equals to 4 superunion mills has this exact sort of anomaly, these symmetries and anomalies that I described. So you can run through the same sort of exercise. Of course, you could work in other dimensions too. I just like 4 dimensions. And then tracking the defect operators in the symmetry TFT across our G flow can lead to insights in anomaly matching. So this is an interesting sort of question you can ask. And so there are, of course, many future directions to ask. So firstly, like, what is this notion of anomaly field theory for the non-invertible case? We had some discussion on that earlier. I think that's something to be debated, but certainly I think deserves some more understanding. It'd be very interesting to have a complete characterization of the Hooft anomalies for non-invertible symmetries in higher dimensions along the lines of the work I described. It'd be very interesting to understand how that extends. These Lagrangian subalgebras are related, of course, to the braiding of these operators in the symmetry TFT that I was describing. Now, I was describing some special set of theories where I know the symmetry TFT, and then I can like get the anomalies for the non-invertible symmetries, using like information I knew about the invertible symmetries, basically. And so it'd be really interesting to extend to cases where I don't have such a picture. I would call those, some people call those intrinsically non-invertible symmetries. The big question, the big interesting question, I think, is to actually explore dynamical consequences for these non-invertible symmetries. And so understanding more such dynamical consequences, I think, is like one of the more important questions in this field. So yeah, with that, thank you very much.
Questions?
Can you say again what you meant by intrinsically non-invertible?
Oh, yeah. So remember I said that the symmetry TFT is invariant under topological manipulations. And so in the examples that I was focusing on, I was focusing on examples where I got to a theory with a non-invertible symmetry from like some sort of gauging or something from a theory that didn't have one. And this is what allowed me to explicitly compute the symmetry TFT as like some, like, it's just like some Digraph-Witten action where I can explicitly compute everything nicely. And so some people call that a non-intrinsic, non-invertible symmetry. That's the, yeah. So I mean, in cases where I don't have such a connection, it'd be, you know, those are of course very interesting as well. So we want to have something that applies to those.
Let's go back to the previous slide. The N=4 case that you're mentioning.
Yeah.
Here, can that be engineered in string theory?
N=4 superunion Mills, yes. Yeah.
So can you see there? Is there some picture for what the symmetry TFT?
Oh, yes, yes. So I should say, like, the symmetry TFT is one very natural way to think about it is from string theory. So in string theory and in holography, like we're usually thinking about symmetries as gauged anyway, and so it's very natural to think about this object of the symmetry TFT in the string theory context. Yes, and you can understand at least, like, for example, like this paper I was mentioning here, like they were understanding how to get at the symmetry TFT in sort of string theory setups where I've engineered some quantum field theory from like either holographically or from like wrapping brains, and like I basically take like the topological terms upstairs in my like, you know, like 11D or 10D action, and then they understood how to reduce those topological terms to get the symmetry TFT for that class of examples. Yeah, so I'm also really interested in that perspective. I think that might be like a really natural perspective or way to think about this, like quote unquote anomaly field theory for a non-invertible symmetry, also from the string theory perspective. Yeah.
So your framework applied to dimensions greater than 2. There's no parallel of the other approaches to dimensions greater than 2.
Well, so yeah, our framework. So the problem is, of course, we have some criteria, right? Like some criterion for like the anomaly. The upshot is it's very computable in some cases. And it does apply to these higher dimensions. So that's very nice. But it's one criterion. It's not the if and only if statement. It's not a full characterization of the anomalies. Like I said, I can't probe all anomalies this way, and it's not like sufficient and necessary. So actually, like doing the sort of hard work to do that full characterization in higher dimensions, it depends on a lot of the details that I didn't have to care about because I was only looking at this one criterion. So there's a lot of things that get more complicated for these non-invertible symmetries between 2 dimensions and higher dimensions. And I could be sort of glib about them in this talk because this condition can sidestep those subtleties, but you really need to care about them if you want a full characterization. So that's kind of why. Yeah.
Is there a way to like state this result in terms of like what sort of like in what sort of 5 manifolds I should consider to detect these anomalies?
What do you mean?
Like you have engineering or like mimicking like interesting topology in 5 manifolds, at least in the case of like 4-dimensional non-invertible defects. Like for 4D theories. And then you're saying like two different like topological configurations should have like the same vector spaces in the symmetry TFT, is that?
Let's see. Okay, I'm not sure, maybe the best, maybe I'm not quite understanding your question. Maybe ask me afterwards.
There are no more questions. Let's thank Emily again.
You should have like, figure of geometric.
What?
Well, let's see.